Let us begin lectures on machine design part 1. This is lecture number 38 and the topic is design of cylinders and pressure vessels. This is the part 3 and the concluding part of the lectures on the same topic. Now in last two lectures we have discussed how to design a cylinder when the cylinder is modeled to be a thick one or a thin one, and also we have discussed how to take care of the effect when the cylinder rotates, also the temperature distributions. Just before going further, let us recapitulate once again what we have learned so far in a very brief while. So let us, for this time being, let us again go back to the earlier discussions and just refresh our memories about the stresses in cylinders. Now the discussion started with the different kinds of cylinders. You see, the cylinders are classified according to the thickness and so this is the thickness and the inner diameter di. So it is divided, if this is t by di, if this is less than 0.1, then we call it a thin cylinder, and if it is greater than 0.1 or equal to, we model this to be a thick cylinder. Now for a thin cylinder we have two kinds of stress. So now let us discuss about thin cylinders. So for thin cylinders we have two stresses. One is hoop stress, which is P. P is the internal pressure, that is, we are designing a vessel which is subjected to pressure from inside. So this is now PR divided by T, where R is the mean radius, because now the inner radius and the outer radius, they are very close. So therefore we model to be the same as the mean radius. So this is the hoop stress, and we have another stress which is longitudinal stress, and this is PR by 2T. So these are the two stresses, and those are now the normal stress. Why normal? Because there is no shear stress involved, and the assumption is that the stress distribution, along the thickness of it, so sigma r, if you remember when we applied for the thick cylinder, here for the thin pressure vessels sigma r is equal to 0. So with these assumptions we have these two kinds of stresses. Now with this stress we can design the pressure vessels or the cylinder for various design for failure criteria. For example, the pressure vessel, if it fails for shear, then we will have to calculate the maximum shear stress. Now that is very easily calculated knowing the hoop stress and the longitudinal stress. So these are the two major formula used for the thin cylinder. Now for the thick cylinder we have a number of design criteria which we use. Now this is for the thick cylinder. Now if it is subjected to internal pressure, then of course whether this is plane strain problem or plane stress problem, the results are similar. But if it is rotating, or if it is subjected to thermal stresses, that is, there is a temperature distributions, then of course we will have to differentiate between the plane stress problem and the plane strain problem. Plane stress problem appears for a short disc or for a short cylinder, whereas plane strain problem is normally taken when the cylinder is too long, because then the normal strain is neglected. Now for the thick cylinder, when it is subjected to internal pressures, as I said, the thick cylinder, that is the stress distributions is independent of the whether the problem is a plane stress problem or plane strain problem. Now when we have any such kind of situations, then sigma r is equal to, that is sigma r is the radial stress, and this will be equal to C1 minus C2 by r square. That is sigma r varies within the thickness. Suppose within this thickness sigma r varies from minus p to 0. So, this is with r, this is r, and this is sigma r, and sigma theta is again taken to be, this is sigma theta is C1 plus C2 divided by r square. Now, C1 and C2 are constants and they are to be obtained from the boundary conditions. Now, if it is subjected to internal pressure, then of course sigma r equal to minus p at r equal to Ri and equal to 0 at r equal to R0. So, these are the boundary conditions with which we can find out the stress distributions, and once C1 and C2 are known, then we can plug the same into the expressions for sigma theta to find out the again the stress distributions in the circumferential directions, and that stress distribution is somewhat like this. So, this is the sigma theta, which again gets a maximum value at the inner radius when it is subjected to internal pressures, and the minimum the outer radius in the and the maximum compressive stress for in radial direction is in the inner radius and 0 at the outer radius. So, these are roughly the stress distribution. Now, this is for the plane stress as well as plane strain problem. Now, once we select the design criteria, that is if it fails under normal the maximum normal force, then of course the design thickness, as we have seen in the last class, that is T, that is the design one, is equal to Ri times under root sigma allowable plus pressure, that is internal pressure, sigma allowable minus pressure minus 1, and so. So, this is the thickness to be designed. Here you see that if P is greater than sigma allowable, then of course no T can exist which will which can be designed, that is no T exists for which this cylinder can sustain this force. So, therefore, if we want to increase the capacity of this cylinder, that is the maximum pressure that the cylinder can withstand, then with this material it is not possible. Therefore, we have to do some other we have to resort to some other techniques in order to achieve a higher strength. That is, if we want to design a cylinder such that a stress that is an internal force, internal pressure more than this particular value is achievable, then we will have to think of other means, and that is what we are going to discuss today. But this is the case where the material fails in normal stress. Now, if it fails in shear, then of course the situation is different, and the formula, you see, if this is fail in shear, then this is so tau allowable divided by tau allowable minus P minus 1. So, this is the design thickness. Again, if P is more than tau allowable, that is allowable shear stress, then this material will always fail in shear. So, we will have to again consider a different technique such that the strength of this cylinder could be enhanced. Then if the material is ductile, so this is the case when it fails in shear. If the material is ductile, then of course this maximum stress criteria cannot be used, and we will have to use what is known as Bernoulli's equations, which I am going to write down. We have discussed in the last class. See here, if you want to have for the ductile material, then this is Ri, then under root under root sigma allowable plus 1 minus nu, where nu is the Poisson's ratio, times p, and sigma allowable minus 1 minus 1 plus nu p minus 1. So, this is the thickness, and this comes from the Bernoulli's equation, and this is valid for ductile material and open-ended cylinder. This is very important. If it is closed-ended, then of course in addition to sigma r and sigma theta, there will be another stress, that is the sigma z, that is the longitudinal stress, which we have not considered here. But if you consider the longitudinal stress, then if you apply the same strain considerations, that is the material fails if a maximum strain is exceeded, then of course we will have to use another formula, Covariance formula, and that looks like something different. That is, here T is equal to Ri times sigma allowable plus 1 minus 2 nu times P divided by sigma allowable minus 1 plus nu times P minus 1. So, this is for the again for the ductile material, and this is closed ended. That is very important. So, whenever we have such conditions, then we can get this proper thickness for which the cylinder is able to sustain this particular pressure P. Again, for a high pressure pipe, we can use a very similar formula as the hoop stress, but now in that case, instead of the mean diameter or mean radius, we will have to consider the outer radius. This is again for the thick cylinder, but a very large pressure, high pressure gas or oil pipes, we use that kind of formula. So, these are for the cylinders which is not rotating, neither it is subjected to any thermal loading. Now, if it rotates, then of course, so let us consider the case when it is rotating cylinder. For the rotating cylinder, of course, sigma r is given by this formula, 3 plus nu divided by 8. Nu is against the Poisson's ratio, and this is rho omega square r square. Rho is the density of the material, omega is the speed of rotation, the angular velocity of the rotations of the disc. Again, this is based on, let me write down, then this is C1 minus C2 by r square, where C1 and C2 are constants which are to be obtained from the boundary conditions, and this is valid, and sigma theta will be equal to minus 1 plus 3 nu by 8 rho omega square r square plus C1 plus C2 by r square. Now, this is the additional stress which appears only due to, so this part appears due to the rotations, whereas this part appears only due to the rotations. But important thing is that this is for the plane stress consideration, plane stress problem. If it is plane strain problem, then the solution looks, the stresses looks different. We are not going to do that, but plane stress problem, for that is, this may be valid for a thin disc or a very short cylinder. If it is a very long cylinder, then we will have to consider the plane strain problem, which looks a little different. Now, this is for the rotating cylinder. Now, if it is subjected to a thermal load, that is now what we have discussed earlier, that if it is a temperature distribution, that is, if there is a temperature distribution, that is throughout this thickness the temperature varies as a function of r. So, this is temperature T, capital T, which is a function of r. Now, if throughout the thickness it varies, and then if we use again the plane stress considerations, then sigma r is given by alpha. Alpha is the coefficient of thermal expansion, which is known, and this is r square. Then the integral is from the lower limit is Ri and upper limit is R, that is the value where we are interested in, and this one is R T as a function of R dr, and there it is a minus sign. So, let us not forget this minus sign over here. So, this one plus C1 minus C2 by R square. Always you see this term remains, C1 minus C2 by R square. This is the basic solutions without any temperature, without any rotational effect. Sigma theta on the other hand looks like alpha E by R square times integral, which is Ri to R, R dr dr, again a new term, this is minus alpha E times T, T is the temperature. You see alpha times T has the dimension of strain and times Young's modulus gives the dimension of stress. So, this is very much clear, that is consistent in dimensions, then C1 plus C2 by R square. So, this is the case for temperature distributions and the plane stress. Again the solution looks a little different when you go to the plane strain problem. We are not going to do that, but this is very important, because normally the pressure vessels are should carry some liquid or some gas, that is some material which at some very high temperature. For example, in the boilers it is expected to carry the liquid at high temperature. So, when the temperature distribution is uneven for the thickness, for the thick cylinder temperature distribution is quite uneven, and in that case the thermal stress may be developed, and that has to be taken into consideration while designing. So, these are very important thing. Now, this is what we have already learned. Now today we are going to learn how to design a pressure vessel for increased pressure. That is, we have seen that there is a limit of pressure which can be withstood by a cylinder, a thick cylinder. For example, if the material fails in tension, that is by maximum normal stress, then of course if the P is greater than sigma allowable, then the material fails. So, this is not expected. We will have to do something where the material can be saved, that is the cylinder can be safely designed. If it fails by shear, then P, if becomes greater than tau allowable, that is allowable shear stress, then it may again fail. So, we will have to design in such a way that the material does not fail even if P is increased significantly. So, that will be the topic of today's discussions. Up to this we have only recapitulated what we have learned so far. Now, cylinders designed to withstand high pressure. How high? That is higher than the limit set by the Lame's equation, Lame's formula. Now, there are two techniques. That is, the first technique is that by compound cylinder. Compound cylinder. What is that? Suppose we have a cylinder and this is a cylinder, the cross section of it. If we take another cylinder of inner diameter which is little bit lower than the outer diameter of this cylinder, this particular cylinder, and then heat it and make the diameter little larger than, by heating the diameter changes, increases. So, if by heating the diameter increases to increases beyond the maximum diameter of this cylinder, and then we put it on the top of the original cylinder here and then allow it to cool. So, after cooling, the shrinkage takes place and the other cylinder fits tightly on the top of this particular cylinder. So, this is the compound cylinder. Also, there is another way of making this compound, that is by press fit, that is we give large mechanical force in order to insert the smaller cylinder with larger outer diameter into the outer cylinder, which has a smaller inner diameter. So, this is the compound cylinder. What happens for this compound cylinder? Here we are going to see that a compressive stress is developed in the compound cylinder. Now, if the compressive stress is developed, then the material is under compressions. So, whenever we apply, so originally it is under compressions, when we apply the external pressure here, then of course the tension develops over here, because there was initial compressions. Now, even with tensions, the maximum value of the tension does not reach to that alarming level. So, this is one way to increase the strength of the cylinder. Sorry. Then we have second method, which is by plastic deformation. By plastic deformation, what happens? We all know that for a material, if we have a stress strain diagram something like this, then if we give initial stress to this particular point, so we increase the stress and let it go up to this point, and then we release the load, then what happens? There will be some deformation, residual, and then if we increase this load again, then what happens? It goes to this point. So, therefore, we see that the maximum load which could be taken by this material has increased. Therefore, it is possible to make the cylinder withstand a high pressure by plastic deformations. But here in this class we are going to study what is meant by compound cylinder and the stress analysis in a compound cylinder. So, now let us see the compound cylinder. We know that if a second cylinder is pressed or fitted on the top of the first cylinder, then a compressive stress develops. So, this is the inner cylinder and a compressive stress developed over here. Compressive stress P is developed. So, now, so this is subjected to external pressure. You see this distance, let us say R1, suppose this is R2. So, the Lamis equation is sigma R is C1 minus C2 by R square, and the boundary condition is that sigma R equal to 0 at R equal to R1, which gives C1 equal to C2 by R1 square, and sigma R equal to minus P at R equal to R2. So, therefore, minus P is equal to sigma 1 is C2 1 upon R1 square minus 1 upon R2 square. So, therefore, C2 is equal to minus P R2 square minus, I am sorry, R1 square R2 square divided by R2 square minus R1 square. So, if you take this again substitute there, C1 will be equal to C2 divided by R1 square, that is C1 is minus P R2 square divided by R2 square minus R1 square. So, in that case if you take help of these two equations, then what we get, sigma R is equal to minus P R1 square R2 square divided by R2 square minus R1 square divided by times 1 minus R1 square minus 1 by R2 R square. Similarly, sigma theta will be equal to C1 plus C2 by R square, and that will be equal to sigma theta will be equal to minus P R1 square R2 square divided by R2 square minus R1 square times 1 upon R1 square plus 1 upon R2 square. So, what is the nature of the stress distribution across R1 to R2? It looks something like this. This is R from R1 to R2, and we see sigma R is always negative and sigma theta is always negative. Sigma R takes a value 0 and goes to minus P over here, as you can see. So, this is sigma R is minus P up to there, and sigma theta is quite large over here and goes to this value. So, therefore, sigma theta takes a maximum value at R1, and that is equal to sorry, these equations will be here. So, this is 1 upon R1 square plus 1 upon R square. Now, the maximum value takes at R1, which you can always verify, because at R1 this is twice P R2 square divided by R2 square minus R1 square, and at R2 this is twice P R1 square divided by R2 square minus R1 square, which is of course lesser than this limit. So, therefore, there is a high compressive force is developed across this width. Now, that is very effective because now we have initial stress which is compressive. Now, we apply internal force, internal pressures, then a tensile force will develop, tensile stress will develop, and this tensile stress, if it is even if it is quite high, but the resultant stress will not be that high because of this compressive stress. Now, let us look at what happens to the outer cylinder. This is so far as the inner cylinder is concerned. Now, for the outer cylinder, again what happens is that for the outer cylinder, it has radius, this is R2, which is the same as the outer radius of the inner cylinder, and this is R3, let us say. So, now it is subjected to a pressure from inside. Pressure from inside. So, now what will be the stress developed? The stress developed is well known, and that is from the thick cylinder formulations, that is sigma R is equal to P R1 square times R2 square times divided by R2 minus R1 square times 1 by R2 square minus 1 by r square, and sigma theta is equal to p r1 square r2 square divided by r2 square minus r1 square 1 upon r2 square. I am quite sorry here because we have taken r3 and r2, not r1 and r2. So therefore, let me write down it again. This is equal to sigma r is p r2 square r3 square divided by r3 square minus r2 square 1 upon r3 square minus 1 upon r square. You see, this is always compressive, and sigma theta is p r2 square r3 square divided by r3 square minus r2 square 1 upon r3 square plus 1 upon r square. So this is always tensile, as you can see. So now the stress distribution is again very well known, that is with r, if the this is r1, this is r2 and r3, then this is the sigma r distribution, and the other distribution is sigma theta. Now this is tensile. So when we see the compound cylinder, now look at the cylinder overall, then what we get, the following stress distribution. Now this is the stress distribution only for the outer cylinder. For the overall cylinder, the stress distribution will be again, if you look at the, this is the inner cylinder, this is the outer cylinder. I have drawn only a part of it. So this has radius r1, this is r2, and this is r3. So therefore the stress distribution will be equal to r, and this is sigma. We have 3 r1, r2 and r3. Then the sigma theta distributions, that is sigma theta will be here compressive, then tensile. So this is the rough distribution of sigma theta. Of course, sigma p, sigma r, that's the radial stress distribution, will be something like this. Here it goes to minus p. So sigma r distribution is something like this. So this is again positive, this is negative, and this is negative throughout. So this is the overall stress distributions only due to the fitting. Now here you see in the inner cylinder, of course we have a compressive stress. Now if we apply again, now we apply here Pi, that's internal pressure. Now we apply some pressure inside. So therefore this, in that case, this could be taken, the compound cylinder could be taken as one cylinder, and only the stress due to this Pi, the distribution of the stress will be equal to, so this is the stress distribution sigma theta only due to Pi. So now we see the resultant stress distribution. Resultant stress distribution is then very clearly seen to be the following, that is here the resultant of this is this one, then here. Now there is a large variations and something like this. So this is the resultant distribution. Now one thing is clear, that here we have a large although we have a large pressure here, but the tensile stress that in the circumferential directions is quite small, and in the outer cylinder of course tensile stress is quite large, but if we select the the pressure, that is initial pressure, properly, then we can select such a way that these two stresses are comparatively same. That is, we can design by a proper manner a cylinder which is uniform in strength, at least roughly uniform, because here it cannot be exactly uniform, it varies from one cylinder to the other cylinder, but it does not vary throughout, it varies, it goes down, again it goes up and goes down, and so on. Now we can extend it to multiple cylinder. Here we have considered only 2 cylinders, but we can go easily to the multiple cylinder. And this is very important because we have saved some material. With one cylinder we have seen that if we go to the higher radius, then effectively all the material is not subjected to any stress at all, and that is a very small stress compared to the inner cylinder. So if we go increasing R, then we are losing the material in fact, because this material is not properly used, it is not properly stressed. But if we have a compound cylinder, then you see that all the materials are, or all the cylinders are stressed to the same extent, and thereby we have saved some material. So that is very clear from this diagram, that how a material saving can be done, as well as a high pressure could be withstood in a cylinder. Now this is about the stress distributions. I have not written down the exact stress variation, which is complicated, but I have only showed that what is the what kind of stresses will appear and what is the advantage of making a compound cylinder. Now remember, in the derivation of course we have used this pressure P, that is the pressure to pressure between these 2 cylinders. We have designated this to be P. Now this was acting externally to the first cylinder and internally to the second cylinder, but what is that value of P? That is very important to know, because all this distribution, that is this distribution and that distribution, will depend on what is the value of P, and this value of P exactly depends on the clearance between 2 cylinders. That is, I have said already that the outer cylinder has inner diameter which is smaller than the outer diameter of the inner cylinder, and this difference between 2 cylinders, this is the clearance between 2 cylinders, is very important, and it is the guiding factor in deciding what is the effect of P. But how to get that value of P is a statically indeterminate problem and cannot be solved unless you consider the strain into account. If you consider the strain, if you that is bring into the strain into account, then what you have is UR, that is sigma theta, is the strain along the circumferential direction, is nothing but U divided by R. That is, U is the displacement along the radial direction, that is radial displacement. And R is the corresponding radius, and sigma R is equal to del U or du dr. Now here we have the following fact, that U for the first case is U is R epsilon theta, and epsilon theta is again, if we use the Hooke's law, it is 1 upon E times sigma theta minus nu sigma R. Now for a cylinder which is not subjected to Pi, now of course we have to remember that we are considering only the only the effect of shrinking. Then sigma theta and sigma r we have to calculate in these 2 points. Now if we calculate sigma r and sigma theta, these expressions are known. So we know that sigma theta for the outer cylinder, that is sigma r theta as r equal to r2 for the inner cylinder, and sigma r for r equal to r2 for the inner cylinder again. And we know we can calculate sigma theta and sigma r for again at r equal to r2 for the outer cylinder. So we calculate these 2 things. So these 2 things are to be calculated, that is sigma theta at r equal to r2 for inner cylinder, sigma theta sigma r at r equal to r2 for inner cylinder, sigma r sigma theta at r equal to r2 for outer cylinder, and sigma theta at r equal to r2 for sigma r at r equal to r2 for outer cylinder. So these are to be calculated, and then we will have to calculate the shear strain epsilon theta and epsilon theta dash, that is for the inner cylinder and for the outer cylinder. Then we can calculate from these 2 data sigma epsilon theta at the inner cylinder and epsilon theta dash at the outer cylinder, all at r equal to r2. Then once epsilon theta and epsilon theta prime are known, then we know the u and u prime, that is the displacement of this point, of any point on it, when we consider the point to lie on the first cylinder, let us call this to be u1, and when it lies on the second cylinder, then we call it u2. So it is possible to calculate u1 and u2 knowing this epsilon theta and epsilon theta prime, and once we calculate that, then the following relation is used, that is u2, that is the radial displacement of the outer cylinder, minus u1. Why minus? Because there will be a compression in the inner cylinder. So inner cylinder, this part will try to go in, whereas outer cylinder, this point will try to go out. So the net displacement will be equal to u2 minus u1, and that will be equal to the clearance between these 2. And once we use this formula, again this is nothing but epsilon theta prime times r2 minus epsilon theta r2 equal to delta, and once we use again the Hooke's law, we can get the value of P. So this is quite easy exercise if you follow these steps. So what we have learned is that here we can take the pressure, we can get a large pressures, remember, because of the compressive stress developed in the inner cylinder, a large pressure could be withstood by the inner cylinder because there was initial compressions. So if we apply external pressure from inside, then a tensile stress is developed, but that tensile stress is to be added to the compressive stress. So therefore the value of the resultant value of the tensile stress is much lower than the single cylinder. So therefore this technique could be used very effectively to enhance the strength of the cylinder. Now this is about the compound cylinder problem. Now let us look at one or two more things. Now here we have considered only the pressure vessels, and those pressure vessels were the pressure was uniform, but in some cases like in tanks or in gravity loaded vessels, the pressure may not be uniform, and we will have to consider the weight of the liquid as such. We have not considered the weight of the liquid in the design so far. So, suppose this is one such tank, and here it contains liquid. So, this is the water level or level, and there is a support, there is a ring over here, and this ring is supported. This kind of tanks you have seen very often. Now, these are the supports. Now, what will be the stress distribution for that? Now, in order to get the stress distributions, we will have to use again the formula we have derived. If this is to be very thin cylinder, thin pressure vessels, then one can use this famous membrane stress formula, that is sigma m by Rm plus sigma T by RT is equal to P divided by T. Now, P here is variable. Earlier in membrane stress, in cylinder design we have considered P to be uniform, but now P varies. You see, at this point the pressure is different. Here at point A pressure is different, point B pressure is somewhat different. Here the pressure is 0 at point O. So, therefore, the pressure varies, and therefore, the stress also varies. Now, what are the stresses? One can expect that there is the stress varies, but it varies continuously, but one expects a sharp change in the meridional stress near the support. How to get that? If we cut a section just above this support and draw the free body diagram, then the free body diagram is now this is the part, this is the water. So, the entire weight of the water above this stiffener or above this ring acts over here. There is a pressure, then P over here, and there is a stress. Then what is that stress? There are two stresses, sigma m and sigma m. Now, if you write down the and suppose this angle is theta and theta, that is this tangent makes an angle theta. So, therefore, if you balance the forces, then what you get is PR square, the total force, that is sigma m, times the area of cross section, that is 2 pi r. The radius here is r, let us say r. So, 2 pi r times t, and sin theta plus W1 equal to P times pi r square. Now, if you take a cut, so this is the equation for this is the stress sigma m here on top of at least a little at a height a little above this ring. Now, if you take a cut again at a point below this ring, that is in the next we are going to consider the cut below it, what we get is the following free body diagram. That is, this is now clear. We get the following free body diagram once we take a cut over here. Then what we get, we consider the lower part here. So, we consider the lower part, and then the stresses developed are again sigma m prime, here sigma m prime, and the pressure over here is, the pressure is same P, and the weight is W2. So therefore the total equation is sigma m prime, again 2 pi r times t, and sine sine theta. Here I want to make corrections here, because we have taken this angle to be theta, so this should be cosine theta and not sine theta as we have written. So this is cosine theta, so this is sine theta, again this is cosine theta, and this minus p pi r square and minus W2 equal to 0. So once we then take these two into account, we see that sigma m prime minus sigma m times twice pi r t cosine theta will be equal to W1 plus W2, that is the net weight of this liquid. So that is very expected, that if we take here, the stress will be more than the stress over here, that is sigma m will be more than sigma m prime, and this this difference will be that due to the weight, and this is the stress taken by this foundations or this particular ring. So this is the stresses in tank and gravity loaded vessels. Now if we have a filament wound cylinder, then what happens, that sometimes we need to get for the light vessels or maybe the thrust chamber in rockets, spacecraft, etc. In that case, we need the vessel to be very light, and that is done by making the vessel of fiber or composite materials. Sometimes we make a very thin metallic membrane and then wrap it with the filaments. So filaments are wire ropes which can take large tensile stress. So if you have this, if you wrap it up the entire pressure vessel by this filament, then a large stress could be taken. So if you consider, say, following case, that there is a pressure vessel and there are filaments over here throughout, and similarly this is wrapped from the other side. So this wrapping depends upon what is the type of this head. So in one direction it is helically wrapped, and then again on the cylinder head it is wrapped, it is taken, is wound, and it is taken to the other side. So there is an integrated pattern of wrapping over here. But if we consider this particular angle, let us say psi wrap angle, then after all the necessary calculations, we can take that this tan psi, if you make out the free body diagrams, which I am not going to do, tan square psi is roughly 2. So with this we can calculate what is psi, and this is about 54.7 degree. So if we make this angle of wrap, then it can sustain the pressure in the same way as a cylinder. So this is very effective technique. Now what we have learned so far, that is, we have learned how to make the stress calculations for a thin cylinder, for a thick cylinder. Then for the thick cylinder, it is not possible to withstand the pressure, very high pressure, with a single cylinder alone. So therefore we go for compound cylinder. In compound cylinder, we wrap this cylinder, that is, we take another cylinder whose inner diameter is little below the outer diameter of the original cylinder, and shrink fit it, that is, press fit by mechanically or by thermal processes. So once this pressing is done, then it develops internal pressures, compressive forces, compressive stress, and then it can take a large tensile stress, that is large internal pressure without failing. So this is very effective technique. There are other cases which we have studied. One is tank and gravity loaded vessels, and the last we have studied the filament wound cylinder. Of course, these are very much useful, but we didn't have enough time to discuss about this. So if you are interested, you should read from some good books. So this is all from today about the cylinders. So in the next class we begin a new topic. So till then, goodbye. Thank you. Dear student, let us begin the lectures on machine design part 1. This is lecture number 39 and the topic is design of brakes. Now there cannot be any doubt that brake is one of the very important members of a machine. The brakes are used normally to reduce the speed of some moving components, that is to dissipate the kinetic energy of a moving system to some other form of energy, for example heat. Normally this is heat. Now there is a very similar component in machines. Normally this is called clutch, but the difference is that in the clutch the two moving parts are brought into synchronicity, that is the speed of two parts are brought to the same, and in the clutches the two parts are both of them are moving, whereas in brakes one part is normally kept stationary, but in both the cases the energy is transferred from one part to the other by means of frictions. So here in this members, brakes or clutches, the friction force plays a dominant role. So friction force is a very complicated force, and normally it is modeled to be a Coulomb frictions, where the friction force is proportional to the normal force applied. So this is very much known to you that how to model a Coulomb friction force, but normally let me point out that in typical situations the friction force, the modeling of friction force is a very complicated task, because the friction is a microscopic phenomena, and in order to bring it into the macroscopic scale, then many assumptions are to be made. So normally we make these assumptions named after Coulombs. So